So the focus of this lecture is to actually go through the above-threshold derivation for a MOSFET. We're going to be focusing this from an MOSFET perspective. We're going to kind of assume that you've actually seen what a MOSFET was, and you've probably looked at one or two of the previous lectures that talk about above-threshold MOSFETs, and are at least familiar with some of the basic concepts. So remembering that in above-threshold, the first big thing that you see is that you have more current than the threshold current, which means that the charge itself will actually terminate some of the field lines as I go from source to drain. Now I've got to actually change in the potential. One of the things that comes out from having this significant change of potential is that the current's moving by drift. Basically, I expect that there's a change in my potential from the source edge of the channel to the drain edge of the channel by more than UT. If it was less than that, then we'd probably sit there and go, yeah, it's relatively flat and it's mostly all moving by diffusion and it's basically a subthreshold model. But we basically get these questions all together. So as a result, I'm going to want to look at a very simple concept of the current is going to be a drift current, and we're going to model it that way. The mobility times the charge at a given position times the electric field at a given position. Now the nice thing electric field is it can just be the first derivative of voltage, so no problem, right? So we're going to begin to look at these questions, and you go, okay, great. Where am I going to get this from? Well, if I look on the other side here, we can talk about the charge at anywhere along this channel, and at this point we're assuming that it's inverted all the way along the channel for this conversation. That is an assumption, right? But from the source to the drain. And so what we'll be imagining is that the charge all the way across will be related to the gate voltage and the surface potential. And in fact, there is a direct capacitive coupling. There's also charge that comes from the surface potential through down to the substrate, which we're assuming is at ground at this point for typical NFET in a typical NWEL process. No problem there. So you're going to have your total capacitance is going to be, remember, your depletion plus your oxide capacitance. So we need both of those things. And we'll utilize these things as we go through this. It'll be very important to look at what the values are at the source edge of this structure, which will basically be related to the source voltage. It's a small offset if you're careful, but pretty much we're gonna work with this. And the drain side, the same sort of thing. Small offset, less than 100 millivolts kind of number. And remember that kappa will be the oxide capacitance over the total capacitance. And I know I'm doing an above-threshold derivation, and this might still startle people that there is a kappa here, because shouldn't it just be gate voltage minus source voltage? And the answer is no. When I talk about threshold voltages, I'm going to be talking about threshold voltages that do not really change with any source bias, so that often means VT0, and that's the typical lore we'll use there. So if I have these two sources, these charges, and I have this charge, well, this actually allows me to ask the question of what is the potential or the surface potential along the device and its charge. And so it actually allows me to talk about what is that, if I take the first derivative of it, I actually can see what is the derivative of potential, the derivative of charge. So this allows me to actually do something very nice with this and basically substitute the structure to be the current is going to be equal to mu and total capacitance Q and dQ dx. So now it's really just dependent on the charge on this. No problem, right? Except we don't entirely have all of the charge, but let's assume that it is some function and we'll work with it. How would I solve this? Well, the first thing I'm going to know is that this is going to be current, and current is in fact a constant with position. It kind of has to. There's nowhere for any charge to be lost in the channel. It doesn't go anywhere. So if carriers are moving, they're going to have to move, the same moves in has to move out. There's nowhere else for it to go. And so that actually turns out to be very, very useful. And I can imagine that if I integrated the current over distance, I'm going to get one result. Okay, and that's basically just going to be current and effectively the length of the channel, or the effective length of the channel. And the other side I'm going to get mobility, which we're going to assume for the moment in this derivation does not have an impact on position. That may or may not always be true, but we'll start with that for our discussion. And integrating Q dQ, because I can kind of integrate over dx. No problem. This is great. And then what are my endpoints? Well, it would need to be the charge at the one end, which is the source end, and the charge at the drain end, which is actually values we do have. Even if we don't know what's in between, we do have the values at the end. So if I integrate this, this is just going to give me basically a quadratic I get a 1/2 out of this, and I get a difference of the charge of the source and the charge of the drain. And so this becomes the core of the expression. By taking these and plugging it into the system, and plugging it in, I actually get something a little more complicated, but basically the same structure. Is going to be, I get the charge, something proportional to charge of S and something proportional to charge of D, where now I'm defining K as mu times C oxide times W over L, and I'm going to get a K over 2 kappa on the outside. And so now, and again, you might wonder, where does all this come from? Well, if you think of it as mu over 2 CT, I'm going to get a CT here, squared, so then I have to be able to go from what is C oxide in this to CT. So this is where part of the kappa will come from. The kappa on the inside comes from exactly what I have on the source and the drain. Cool, so everything works out. When I'm above threshold, this will be slightly different, except that the fact that QD, of course, was always had to be greater than 0 by the simple model. And, QD sort of being equal to 0 will define saturation. If it's less than that calculation, then I'm definitely going to be in saturation. So I think this term might actually be better if this was just an equal sign. Okay. But if I do that, then I can actually get an expression for what the drain voltage would be in this situation. And if that's true, and if that's hold, or I've crossed that situation, in other words, the drain voltage is bigger than that, now my MOSFET, in the MOSCAP then is, as we talked about, is actually in subthreshold. It's kind of being, and so the whole behavior is between depletion and inversion, but the math still works. And then I would still end up getting an approximation where I get the current is related to just the gate and the source voltage. Now there can be an early effect on this. Did not actually add that into this, but basically these are where your expressions are going to come from. The derivation is not particularly difficult. It is particularly challenging in making sure you understand the physics leading into the math. And if you keep the accounting of all the details correctly, it actually works very nicely. And so it turns out that it's still a very intuitive way to talk about the derivation for above threshold, similar to like what you would get above subthreshold, having a very straightforward and sort of intuitive derivation in the overall approach.